So that last example and the one that I left for you to do at 410 illustrate just a few instances of reaction stoichiometry calculations. Numerous variations on the beginning and ending computational steps are possible, depending upon what particular quantities are provided or sought, volumes, solution concentration, and so forth. You can calculate the amount of reactant needed, you can calculate the amount of product produced, and all the different, for each one of the different reactants or the products. All these calculations share a common essential component: the use of stoichiometric factors derived from balanced chemical equations. Right? The other thing is your periodic table, where you've gotten the mass of the individual elements to form so that you know what the molecular weight of each of those is. This flow chart depicts the various computational steps involved in most reaction stoichiometric calculations, in terms of density of something or the mass of it, giving you the moles and the volume or the number of particles, different ways for you to get the number of moles of these different ones. And then from the balanced equation, you get the moles of one and the moles of the other required. Now let's talk about reaction yields. The relative amount of reactants and products represented in a balanced chemical equation are often referred to as stoichiometric amounts, of course, because it's a stoichiometric equation. All the exercises that we talked about already involve stoichiometric amounts of reactants. In more realistic situations, reactants are not present in stoichiometric amounts. So consider this one right here. You got one slice of cheese, 2 slices of bread for one sandwich, right? Now, if your loaf of bread contains 28 slices of bread and one package of cheese has 11 slices, you can prepare 11 sandwiches, right? That's all you can provide. You're going to have some bread left over. So all the provided cheese would be used, and you'd have 6 slices of bread left over. The number of ingredients in the sandwich has been limited by the number of cheese slices. Cheese then would be the limiting reactant. The limiting reactant will always be entirely consumed, thus limiting the amount of product that can be generated. The bread slices have been provided in excess. Bread is the excess reactant. Okay? And so here's just exactly what can happen in a balanced equation, okay, to give one sandwich. Here, with this right here, you have 11 sandwiches and 6 left over. And it works the same way with these different reactions. Okay? You've got 3 moles of this and 2 moles of this. Since this is a 1-to-1, that means this is the limiting reactant and this is present in excess. Okay? So you have 6 moles of HCl can be produced. 4 moles if this was the one. So the smaller one is the one that determines how much of the product that can be produced. Cl will be consumed once 4 moles of HCl are produced, and the unreacted will remain. So chlorine is the limiting reactant, H2 is the excess reactant. So here's what we have before the reaction and then after the reaction. 6H2, 4Cl2, 6HCl, 2H2. The amount of product that can be produced by a reaction is calculated per the stoichiometry of an amount is called the theoretical yield. The amount of product obtained is actual yield, and it's often less than the theoretical yield. I've had some reactions that I was lucky to get 25% reaction yield, and if it's a multi-step reaction, it just keeps going down and down and down as you go through those. And the reason for this is you can have competing side reactions, you can have incomplete reaction, or a product that's very, very difficult to recover. So the percent yield then is the extent to which a reaction's theoretical yield is achieved, and is commonly called the percent yield. It's the actual divided by theoretical times 100. When calculating percent yield, both yields must be expressed using the same units, okay? Number of moles, grams, something like that. So these units will cancel out. Upon the reaction of 1.274 grams of copper sulfate with an excess of zinc, you end up with 0.392 copper metal was obtained according to this equation. What is the percent yield? Well, this right here, this is how much copper sulfate you started off with. You first find out how many moles that is. And you get that by dividing 1 mole equals what its molecular weight is. And that tells you the number of moles of copper sulfate that you have. It's a 1-to-1 relationship. That's what the coefficients are. There's 1 in front of this one, 1 in front of this one. Therefore, this ratio is going to be 1-to-1. And we know that copper itself has an atomic weight of 63.55. So that means your theoretical yield is 0.5072 grams. Now back to here, we only obtained 0.392 grams. So the percent yield is the actual yield divided by that theoretical yield that we just calculated, times 100. So the actual yield was this 0.392 grams. What the theoretical yield was 0.5072 grams times 100 gives you a 77.3% yield. That's not that bad, not that bad. It's always better when it's closer to 100, but that's not too bad. Now, quantitative analysis is the determination of the amount of concentration of a substance in a sample. There's 2 main ways that we in the chemistry laboratory determine that. One is by titration, and next week we'll be talking quite a bit more about that because we'll be doing acid-base titration, and then gravimetric analysis. Gravimetric just means it's based upon weight, okay? So a titration involves 2 types of solutions. You have your titrant, which is a solution containing a known concentration of one reactant, and the analyte. This is a solution containing a reactant of an unknown amount or concentration. Okay, so what you do is this right here is in a beaker below a burette filled with this, and then you closely monitor, follow the reaction of how much of this you add so that this is completely reacted, okay, the equivalence point of the titration. And we determine that by indicators. Some of the best ones are if you have a pH meter or something that imparts a color change at or very near the equivalence point. The volume of titrant actually measured is called the endpoint. The difference between the equivalence point and the endpoint should be negligible if you want to have a valid system. So for example, if you're going to titrate aqueous HCl, and the endpoint was reached with 35.25 milliliters of 0.25 moles of sodium hydroxide. So this is the reaction. What's the molarity of this material right here? Okay, so the volume of this we know. The molar concentration is determined by dividing this in terms of milliliters by knowing 1 liter equals 1,000 milliliters, right? And we know that the molar concentration of that per liter. So this tells us how many moles of NaOH we have here. Then we have 1 mole of HCl per 1 mole of this. That's the 1-to-1 reaction, right? So therefore, multiplying those together gives us this as the number of moles of HCl that was present in our analyte solution. So the moles of HCl divided by the liters of solution gives you 0.176 moles, right? Gravimetric analysis is where a sample is subjected to some treatment that causes change in physical state of the analyte and permits its separation from the other components. A lot of times these will be something that you has precipitated out, and then you vacuum filter it and dry it, and then you weigh what is left in terms of the final material. And this is, as I said, this is typically done by separations of a precipitation reaction. For example, if you have 0.4550 grams solid mixture containing magnesium sulfate dissolved in water and is treated with an excess of barium nitrate, you get a precipitate of barium sulfate of 0.6168 grams. Okay, what concentration, what's the mass percent of magnesium sulfate that was in the mixture? So your mass here, you have to determine how many moles. That's this first step right here. Then you look at the equation. It's a 1-to-1 type of reaction there for the coefficients. Then what you do is you have the number of grams per mole for your product here, right? So that gives you 0.3181 grams of magnesium sulfate. So the mass percent times the example gives you this amount right here times 100. So 69.91% reacted out of that solution, right? So the elemental composition of hydrocarbons and related compounds may be determined by gravimetric analysis, known as combustion analysis. Essentially what you do is you weigh the sample, heat it to a high temperature under a stream of oxygen gas, resulting in complete combustion to yield gaseous products. If you can measure the pressure that you generate and you know the volume, you know how much you have produced. Okay? So you're going to get carbon dioxide and water vapor out of this. And if you put it over something that selectively absorbs the water or something that selectively absorbs the carbon dioxide, the mass of the absorbed product can then be used as an appropriate stoichiometric calculation to derive the moles and the mass of the relevant element. Polyethylene plus excess oxygen yields this right here. And this is the empirical formula of polyethylene. And so what you do is you go through this whole process right here to give the C to H ratio and ending up with the empirical formula. And it works through the steps right here. This number of grams of carbon dioxide are produced. This number of grams of water are produced. So you get the moles of each one. 2 moles of this to 1 mole of this. So the empirical formula then would be CH2, right? Okay. And that's the end of that chapter. In this chapter, what you should have obtained is information about what chemical equations are, how to balance equations, oxidation number assignment for atoms and ions, and how to use that oxidation number to balance equations. Okay, and there's 9 steps involved there. The types of reactions and examples of each one. And then the last portion has been how to use these equations, coefficients, and molecular weight to determine the amount of reactant needed, the amount of product produced, the theoretical reaction yield, percent reaction yield, and you've seen different ways using gravimetric, titrant, and other ways in order to find those numbers. And that concludes Chapter 10, and we can go on now to, and don't forget, there are other homework problems associated with this, and then there's also the lab.